Hello, everyone. Welcome to our webinar today. My name is Daliana, and here we have Ann Holler. So today we're going to talk about AutoML for deep learning with Ludwig. And maybe let's wait for a few seconds for more folks to join. And you might see we have some polls here. Don't be shy. Tell us whether you have heard of Ludwig before. If you have used Ludwig, what was your experience? And I'm very excited today because today is the first time we have a Ludwig contributor to talk about her experience using AutoML for deep learning. And would you mind go to the next slide? So Ann Holler, she's a Ludwig contributor and advisor at Eloti. And I'm Daliana. I'm a senior data scientist at Predibase. So before we get started, just a reminder that all the lines are muted. And if you want to watch the presentation again, today's session is recorded. And if you have any questions during the recording, you can type in the chat, and we have folks from our team to answer the questions. And after Anne's presentation, I will give you a quick demo to show you how to do this in our platform, and then we will take questions. And if you are curious about our platform, you can go to predibase.com to request a demo later. And Ludwig, at Ludwig, we also have a very active open source community. We have a Slack channel. So if you are a Ludwig user, or if you're interested in Ludwig, please join the Slack channel. And if you want to also share your experience with Ludwig, you can message me in our Slack channel. Let me know, maybe you want to present in our next session. That would be all. And take it away.
Okay, thank you, Daliana. I really appreciate being here with you, and thank you to all the folks on the webinar. I want to start with a little bit of background information relevant to this talk on exploring AutoML for DL with Ludwig. The first part of the background is that the webinar content I'll be presenting today was drawn from the following blogs we wrote in 2022. So wanted to shout out to my co-authors on these blogs and all the cool stuff that I got a chance to work on with you guys. So thank you very much. And then I also wanted to mention a personal motivation for this work. I had worked in the Michelangelo ML platform team at Uber, where I was lucky enough to get a chance to meet Piero and Travis from Predibase. And I saw examples where the struggle is real to efficiently create a production DL model that meets team accuracy and maintainability goals. So I just was excited to explore that area. So another little bit of background in case some of the folks on the webinar are not familiar with Ludwig. So Ludwig is an open source declarative machine learning framework. And so it's very easy to get started. I mean, a minimal start would be just to give a list of your input and output features, their name and their type, and let Ludwig by default choose everything else for you. So, you know, it's easy to get started, but there's also an ability to have an expert level of control. So, you know, you can modify that YAML file that expresses things to add in what encoder you want it, to add in what training parameters you want, to add in what model you want, and so on. So it's easy to iterate, and it's easy to bring in more and more levels of control. And finally, it has a bunch of advanced functionality associated with it, including hyperparameter search, a number of state-of-the-art models, and the ability to do distributed training. The core modeling architecture that Ludwig uses is encoder, combiner, and decoder. So the inputs are encoded according to their type and a set of pre-processing rules and so on. The combiner is the basic, you know, model that you're using for taking those encoded items and learning from them. And then the decoder is the process of producing the output that you're interested in your model predicting. As I said, Ludwig has a bunch of sophisticated tools connected with it. One of the key ones from the standpoint of AutoML is hyperparameter search. So Ludwig supports hyperparameter search at scale on Raytune. Raytune is part of Ray, the open source compute platform for scaling AI and Python workloads. So, Raytune gives lots of power to Ludwig. So this is the spoiler slide. This is what the talk is about. So in 2022, Ludwig was extended to include deep learning AutoML for tabular and text classification datasets. In experimental studies, the best models produced by Ludwig AutoML for tabular and text classification datasets were found to be competitive with published manually tuned models. So we're excited about this. And this webinar will deep dive the Ludwig AutoML context, design, development, evaluation, and use. And then at the end, we'll provide example links to 36 different data sets run through AutoML. And we'll give brief pointers on how you can enhance Ludwig AutoML if you want to. So this is the outline for the webinar. So let's start with the context. So why AutoML for DL? Well, every day we see evidence that DL models can deliver world-class results for a variety of problems. So, people want to use deep learning. But it turns out that developing effective deep learning models can be difficult and can be expensive. There's complexity around, feature data typing. There's complexity around model selection. There's many models that people have developed that are available that are good for different purposes. There's complexity around model hyperparameter tuning. Turns out that it's very important to do good hyperparameter tuning for deep learning models. And, added to this complexity is the additional tax that every time you want to do an exploration of DL, you're typically training with GPUs. GPUs are expensive, as we all know. So that double whammy of complexity and high cost for exploration makes things hard. And I've observed firsthand that getting to an effective initial model, for example, for tabular data, can be harder with deep learning than with non-deep learning. So the goal was to create a deep learning AutoML that would capture the heuristics and best practices around developing standard DL models. Wanted to use standard DL models to leverage shared experiences and knowledge in the community. And we wanted to obtain effective models efficiently with reduced human toil and reduced compute resources. So that's why we want DL AutoML, but why is Ludwig the right way to platform for doing this? Well, as we already discussed, Ludwig provides a simple, powerful, extensible framework for creating DL models. It has the declarative API, makes it easy for the AutoML layer to create and iterate configurations. The encoder, combiner, decoder architecture makes it easy for AutoML to kind of put together pieces, parts, to create things to explore. And the platform includes the scalable, sophisticated hyperparameter search using Raytune. Equally important to all of this technical stuff is the social stuff. The Ludwig and Predibase community is insightful, helpful, and supportive, and that really helps a lot as well. So let's just cut to the chase and look at the functional overview of the feature, and then let's dive into what's behind that functional overview. So here is what you do. Here's how it works. Basically, Ludwig AutoML automatically generates a tuned DL model with the following inputs, operation, and output. It takes your data set with train, validation, and test splits. It takes the target column that you want to predict. It takes a time budget for doing the search. And it takes customization options that you may want to specify around the training that you're doing for AutoML. Once it has these inputs, it infers the input and output feature types. It chooses a model architecture. It selects the hyperparameter searches and ranges, and it launches that search on Raytune GPU workers, which you supply, and compiles the results that it gets from that search. At the end of that search, it outputs the best tuned deep learning model, along with all the other models it explored for your comparison with the trial metrics and evaluation statistics. It gives you the packaged model artifacts that will allow you to have flexible serving options with that model and allow you to look at the model in detail to understand it. And it gives you the training configurations so that if you chose to do further exploration, you would have the usable training configurations to do that further exploration. So here's basically a simple example of exactly calling AutoML. So this is on the Mushroom Editability database, a data set, and line 11 is basically the AutoML call. So we're calling it on that data set. That data set has been split into, train, validation, and test. We're giving it the target field to predict. We're giving it the time limit in seconds. We're setting tune for memory. We'll talk about this later in the talk, an option, a user specified option for whether we want to try to respect the GPU memory when we're trying to train. And finally, we're giving it some user config. So this is it, the one line thing that launches the AutoML. So Ludwig takes that input, uses its heuristics to create a hyperparameter search configuration, and then runs that search on RayTune using async hyperband for that specified time limit. The result is the set of models along with the hyperparameter search report. You can look at that search report manually, or you can post-process it with the various Ludwig visualization tools. And this is just one example of a post-processing tool that Ludwig has for visualizing the hyperparameters. So what's behind this, one-liner? What is the design vision and goals? How did we develop it? How did we evaluate its performance? So the vision, the rainbows and unicorns of this was, we wanted it to be simple and economical to use. We wanted it to produce high quality results that are easy to understand and refine. And we wanted it to return the tuned model to allow the user to have serving flexibility. So with that vision, we had a set of goals. We wanted the system to be data informed. We wanted it to use feature data analysis that we had validated. We wanted it to use heuristics we had derived from historical model training runs. We wanted it to be domain and resource specific. So for the given domain to be applied, have AutoML applied, and for the resources that the user is giving to AutoML, it would build an appropriate DL pipeline, including model selection and the search space. We wanted the user to be in the loop, so the user could influence the search, so the user could iterate on the results of the search. And we wanted it to be glass box. We wanted it to produce these standard, accessible, tunable models, not some of the opaque closed models that are generated by many AutoMLs that have a different set of goals. So the key challenge to achieve this vision and these goals was to identify those heuristics that would efficiently and automatically produce Ludwig models that have the accuracy competitive with manually tuned, publicly reported model results. So we had a strategy for trying to achieve that vision and goals, and that was to start with develop target domain heuristics using a collection of diverse publicly available data sets in that domain. And so we would implement the feature data type heuristics by creating code that would match the types chosen by human experts for those data sets, while supporting overrides for special cases where it's hard to automate the choice of data type. We would run an extensive set of hyperparameter training experiments across those data sets to verify that through that extensive set of hyperparameter training experiments, we could get models that were competitive with manually tuned models produced for those runs. If that's true, which we would expect it to be, we would analyze those runs for patterns to exploit to produce similarly competitive models automatically, with the idea that those heuristics would work well for other data sets. And then we would basically sanity check the resulting heuristics by running AutoML on these data sets we use to create it. So this is kind of like running your model on the training set. This is just making sure that the heuristics work well for the data sets for which it's trained. Then we would declare victory, say we were done, and then see how we did by evaluating AutoML for the target domain by running it on a different collection of diverse publicly available data sets, and see if the models were competitive with manually tuned models produced by those runs. So we started with tabular data sets as the domain of interest because for tabular data sets, they're interesting from a business point of view. In many cases, it's easier to create a non-deep learning model for them than a deep learning model. And also, there's not really the opportunity for fine-tuning pre-trained models in this area because there's not kind of a technique for doing that. We developed the heuristics using these 12 data sets. We tried to choose data sets that were diverse in terms of the task. So 6 of them are binary classification, 3 are multi-class classification, and 3 are regression. They are large data sets, or they have varying sizes, but some are quite large and some are relatively small, with a varying number of columns. And those columns have varying types in terms of percentage of numeric input columns, for example, and percentage of category input columns. So given this set of data sets, we started with running that exhaustive-ish, large search on the three tabular model architectures that were available in Ludwig. That is TabNet, which is a Google model that uses sequential attention for interpretable tabular learning. We use Tab Transformer, which is from Amazon, which applies self-attention method to learn tabular embeddings. And we used Concat, which is Ludwig's default architecture, which concatenates the encoding layer output and runs the results through a fully connected layers. And for each of these model architectures, we searched across the hyperparameters that were relevant to that model architecture, and we searched a big range across those hyperparameters. We wanted the search to be thorough, so we used skop hyperparameter search with each trial running up to 300 epochs, with early stopping set to 30 epochs. We really wanted to make sure we could find competitive models with this large search. This consumed thousands of hours of AWS time on G4DN 4X large. These are T4 GPU machines, which we consider to be kind of a sweet spot as far as getting efficient ML GPU resources. And by the way, resource management for DL is a related topic to the topic in this talk, and there's some references at the end of these slides if you're interested in that topic. But anyway, after this process, we did get best models for these 12 data sets that were competitive with publicly reported manually trained models. So now the question is, how can we take that experience and find the characteristics we can exploit to automatically produce those models with much less compute? Well, the first thing we did was choose TabNet as our model architecture for AutoML for tabular data sets. We chose TabNet because it was the most accurate on average across the data sets of the three model architectures we explored. It scaled efficiently as data set width increased, particularly compared to Tab Transformer, and it had the best train time to model performance ratio in most cases. So once we had settled on our heuristic being to use TabNet, we looked at the TabNet hyperparameter search ranges and narrowed them down to values that were associated with the most accurate models, so basically reducing the search range there. We decided that AutoML would launch RayTune for 10 trials by default using async hyperband strategy so that it would be able to stop unpromising trials, which is part of that strategy. And then the final thing we did, and we were actually surprised by this, we did discover kind of transfer learning for tabular data sets. And this really involved the idea that if you have a data set X and you have the best model that you found for that data set, and it has a certain set of hyperparameter settings, and you have a similar data set Y, uses the same model, has a similar set of percentage of numeric columns, for example, so some similar characteristics, and you start your search with the data set, with the hyperparameter settings that you use to get the best model on data set X, that first model that you get for data set Y will be pretty close to its best. So it really speeds up the search process to kind of leverage the settings that you've seen previously work well for similar data sets. And so this transfer learning of hyperparameter config settings is an option in Ludwig AutoML for tabular data sets. So we have a little database in the Ludwig code of previous best models for data sets and their characteristics. And when this option is turned on, it uses that to seed the hyperparameter search to start a trial with that set of settings. So next we took those heuristics and we sanity checked them on the 12 heuristics development data sets. And we would expect it to do well here because this is the way we formed these heuristics. And we ran these for only 1 hour, so not thousands of hours. So for a 1 hour search, all but one of these 12 produced competitive models. The only one that didn't was Mercedes-Benz Greener, which showed signs of overfitting. Its validation score was actually better, but its test score was worse. So that's kind of a known challenge with this data set. So we considered this a positive result, and we were ready to really put this to the test by running our algorithm, which we had declared victory on data sets we'd never seen before. So we chose 9 data sets that weren't included in the heuristics development group. These are the 9 we chose: 3 binary class, 3 multi-class, and 3 regression task data sets with a variety of number of rows, variety in columns, and we ran the algorithm on these. And we were able to get competitive models with respect to manually tuned, publicly reported models with a time budget of 2 hours. So, way better savings in terms of compute time and human toil than developing these models from scratch, we would claim. And you can see the final column gives the score that we get using that transfer learning option that lets you start the hyperparameter search with the best settings from a previous model of a similar data set type. So you can see the benefits there as well. So anyway, we were kind of happy with this, and we wrote a blog on this. We were psyched. So we got, I guess, cocky and decided to try developing AutoML for a second kind of domain. And the domain we chose was text classification. A, important product, and B, it can exploit fine-tuning of pre-trained models. So we thought it would be interesting to see at least if our procedure for creating AutoML would work well here. So we basically developed the heuristics using these 10 data sets. These are different kinds of classification problems: sentiment analysis, topic determination, emotion and hate speech recognition, binary and multi-class, different numbers of rows. And here, we don't talk about different numbers of columns. For text classification, there's one column. That's the text you want to classify. And then there's the output column. But what you do have is diversity of the number of tokens in that column. So here we characterize the number of tokens per column in terms of the max, the average, and the 99th percentile for these different data sets. So you can see diversity there as well. So we formed an initial set of heuristics for the text classification data sets based on various published work, but most notably based on previous work done in the Ludwig community on the Ludwig benchmarking toolkit, which is a very cool product. Check that out. But basically, that case study looked at a wide variety of different scenarios, took 9 text classification data sets, ran them for 7 model types across 4 kinds of classified problems to show how the benchmarking toolkit could, get those results and store them and allow query of them. So we were able to leverage a lot of things learned from that work. So based on that work, we decided that our initial, AutoML would be based on the BERT-based model type. So the LBT study had looked at 7 model types, but BERT-based produced the best model for 5 of the 9 data sets that were used, and very good models for the remaining 4. So we just thought this is really already been shown in this previous search to be, a very good basic model type for AutoML for text classification. We chose the batch size search range based on, Google's recommendations for BERT-based in terms of search range. We set the learning rate search range to be low. These were the values cited in various sources to avoid, forgetting. And we used the AtomW optimizer previously. We've been using Atom, which was Ludwig's default, because of the fast AI comparison of these two for this use case. And we reduced the number of hyperparameter search trials to 5 to match the smaller search pace we're using. So you can see there's a pretty big difference here in terms of just the initial heuristics from the tabular data set heuristics: pre-trained model, small batch sizes, low learning rate, different optimizer, fewer search trials. So, sorry, I'm pushing this, oops. Sorry, I was pushing the button, it was a little delay there. Sorry, so the initial heuristics fine-tuning BERT-based model type yield competitive models for 3 of our 10 data sets in 1 hour, so yay. However, the other 7 failed with out of memory on the T4 GPU, which has 16 gig of GPU memory. So, our next job is to tweak our heuristics and develop them to understand how to handle this. And so stepping back, before we say much more here, I'll just mention that BERT-base is a big model. It has 110 million parameters, much bigger than TabNet. I mean, maybe you wouldn't think it's big if you use ChatGPT, but it's big in this range. And it's a transformer model, so it has quadratic behavior with respect to the input token length. So those two things will be relevant as you see our journey to improve the heuristics for text classification. So the first thing we did is we said, oh, you know what? We kind of expected that there'd be problems fitting into memory. We'll turn on our tune for memory option. So we had created a tune for memory option for AutoML, which would look at the platform that you were going to run your AutoML on, see what the GPU memory size was, look at the search space you were intending to run, and what it estimated the model size would be during training in that search space, and would reduce, the hyperparameter settings accordingly, particularly batch size range, so that it would fit in, the search would fit inside of the GPU in terms of the model fitting inside the GPU. But unfortunately, that didn't immediately work because our model size estimation had a little, it was missing something, basically. It was missing the optimizer bytes per model weight. So we improved its model size estimation. The second thing we did was we actually stepped back and said, oh, look, one of the things it likes to do is reduce the batch size range. But if we look at the LBT results, the models were more accurate if you first tried limiting the input token length before you tried reducing the batch size range. And certainly if you limit the input token length to, let's say, the 99th percentile of the input token lengths, you're still getting good coverage, but you can, in many cases, get a much smaller model size in memory. So we tuned the heuristics for tune for memory to capture this as well. The next problem was that even when you didn't run out of memory for the text classification model, the epochs, which is going through the entire training set and tuning the model, took really long. I mean, they were like glacial. I mean, some of them, it depends on, they basically saw this quadratic behavior. So if it was a large and wide data set, it might take hours to get through an epoch. So the hyperparameter search couldn't be very effective because it couldn't reduce the time very much if it couldn't even get a read on the quality of the model it was getting for such a long time. So we switched from epoch-based evaluation to sub-epoch. So you could get through, you could have two, checkpoints, let's say, during an epoch, and you could evaluate if you've only looked at half the training data, see how good the model is, for example. So basically, we found that this worked well and allowed a good read on the models in a much shorter time. And so we updated the way tune for memory works to also set the number of checkpoints per epoch, depending on how much data there was, in order to get a quicker evaluation of the quality of the model. Secondly, in this area, we reduced the intermediate evaluation overhead, which used to run on the full training set, by introducing an option which tune for memory sets to look at a smaller percentage of the trained data to evaluate. Next, we reduced we revised the way the hyperparameter search worked with respect to model evaluation. So this is a little bit weird. This is a general problem, but we didn't notice it until we were working on this project, which was if your hyperparameter search is optimizing for something like, let's say, minimizing loss, but your evaluation metric is, let's say, Jacquard, because Go Emotions produces a set and uses the Jacquard, you may have a slight mismatch between what you're looking for when you are training and doing your hyperparameter search versus how you're going to evaluate the model. So we fixed that to make those two consistent. So then we did a number of miscellaneous things. We tuned the training loop. We set the max epoch count to avoid continuing to search beyond epochs that tended to have value. We reduced the hyperparameter search ranges. We limited the maximum number of trials to the combination of the hyperparameters, since sometimes tune for memory had reduced that set greatly. And finally, we said, you know what? It doesn't make sense to have a one-size-fits-all time budget in this case, because there's such a big variation in time depending on the width and length of the data set. Let's use a time budget that fits that size rather than just trying to run all the things with the same time budget. So I'm just going to step back here and say at this point that I had thought that creating Ludwig AutoML for text classification would be easier than Tabular, and I was completely wrong. Okay, so we had this set of heuristics. We've done all of this, and now we're ready to sanity check them on our 10 heuristics data sets. We did that. We used the time budgets that you can see in that second column that were set based on the length and width of the data sets. We enabled tune for memory for the 7 data sets that that got OOMs when we first ran our heuristics. And then those other columns are showing you the impact of the tune for memory in terms of setting the maximum token length, in terms of setting the number of checkpoints per epoch, and then shows you how many checkpoints were completed and the average seconds per epoch, just to get a sense of the complexity here. So basically, we did this, and the sanity check runs were competitive with those time budgets and those tune for memory settings. So we felt good. Now we were ready to try this on the data sets we hadn't seen before. So we chose an additional 5 data sets that weren't included in the heuristics development set listed here, both binary and multi-class classification problems, different numbers of rows. They all have pretty large maximum input token lengths, but have some variation in the average and the 99th percentile. So we chose time budgets for this AutoML runs for these data sets we hadn't seen before, based on scaling our experience with the data sets we had seen during the creation of the heuristics. So we knew that for these large data sets, we needed a large time budget, and for these smaller data sets, we could get away with a much smaller time budget. And we chose the scale based on that. And then for all of them, we enabled tune for memory because all of them had a large number of tokens. And you can see that the impact it had on tune for memory had on token length, checkpoints per epoch, and so on. All of these validation runs produced accuracy competitive with manually tuned, publicly reported models. So yay, this was a good experience. So that's sort of the stuff we did in 2022 to create AutoML for these 2 domains. Let's now talk about how you can use it for your data sets, or how you might want to work on enhancing it. So we talked about the basic, we gave an example near the beginning of the basic API to create AutoML search configuration and run it. So this is the kind of example of the basic API. You could add an additional user config parameter to override any of the attributes that AutoML is going to use to do its search. But the second API that we hadn't mentioned yet, which is really quite useful and helpful, and I used it a lot, is this create auto config API. So the deal with create auto config is it creates the AutoML configuration that it would pass to do the hyperparameter search, but it doesn't actually run the search. So what's cool about this is you can use it to kind of manually inspect what AutoML is going to do, make sure you like it, use user config to override any parts you don't like. You could use it to basically start from there and add things to it. So it's just a really handy thing to do. So anyway, you'll see that user config could be helpful here. I give a link to an example where the automatic type selection for a particular data set wasn't what the user wanted, and they were able to override it with the user config parameter. So basically, here's the links to all of the experiments that we did in terms of, these are all of the AutoML execution scripts for the 21 tabular data sets and the 15 text classification data sets we used for AutoML development and validation. So all of the work we've shown you here. So these are all in the experiments repo, which is under Ludwig. These are just links to those directories in that repo. So you see lots of different examples. You'll see how we set things. You'll see examples where we did use user config and so on. So I think these will hopefully give a lot of things to look at if you want to run AutoML on your own stuff. So what if you want to extend Ludwig AutoML? That would be great. Please do that. So I mean, there's many opportunities to enhance it. I guess a few examples off the top of my head are, one is to improve the handling of imbalanced output features. I looked at the, check-ins since my last check-in was on in July, so haven't been as active recently, but I looked, there's a lot of recent work in this area. So if you look at our tabular results, even though they're good, for things where there's a really imbalanced output, we may not be doing so well on the the rare, predicting the rare thing. So I mean, there's a lot of work in the area, but it's a hard problem. So undoubtedly there's more things that can be done there. You could retarget AutoML for new kinds of domains, new data sets, for example, image data set. The AutoML's code right now recognizes that a feature is an image feature, but doesn't have any code to actually, at least the last I knew, to actually do AutoML for image data sets. There's some pointers here to the Ludwig code that decides whether it's a tabular or text domain or even an image domain. And there's some links here for code that decides what the fields types are. So just a few selected references. So the first references we saw at the beginning of the talk, they're the ones that are covered in this talk. The second set are around cloud resource management for deep learning, kind of a big topic there as well. So that's the Ludwig changes. I think Daliana would like to share the cool things that are done for taking Ludwig and bringing it into Predibase and making it an enterprise experience there.
Thank you, Anne, for the great presentation. So I will share my screen and give you a quick demo of how does it look like if you want to use Predibase to manage your data, manage your entire ML ops process from end to end. So, okay, window. Are you able to see my screen?
Looks good.
Okay. So this is what our platform look like. It's very easy. If you want to upload your own data set, for example, you can connect your data from Snowflake, Amazon 3, GCP, wherever it lives. And for this example, I uploaded the data set from my local directory, and you can do it here. And for the demo, I'm going to use a data set already uploaded. So this is one of the data set in Anne's presentation, use the BBC News data. So once your data is connected, we're going to create a model. So before we create a model, you want to create a new model repository. So let's just call it BBC News demo. The model repository is a Git-like repository where it's easy for you to track model lineage and performance. And just like what you've seen from Anne's presentation, deep learning model or any other type of machine learning model takes a lot of iteration. So we make it easy here. And here you have a few options. If you know what type of model you want to train, you can build a custom model. We also provide a set of baseline models. So it's easy for you to quickly get a baseline for your data set. And here I will show you how to use the AutoML feature in Predibase. The Predibase, the backend is the same with Ludwig, so you get a benefit of using the Ludwig models here. So let's just call it AutoML version AutoML 1, and you can select the connection, how you connect to your data before. We're using the BBC News dataset. And the task is we want to categorize those news. So if you scroll down lower, you can see what are the features you want to use. And when we click next, you have the basic default. And so here, if you select the suggested configuration, that's how you can use the Ludwig AutoML in your Predibase configuration. Here you can see the model graph, parameters. You can train with a hyperop, etc. So now if you click train, this model will be queued. And for this demo, I'm going to just show you the results of a BBC News model that I have trained before. This model. So you can see the best performance model is this one trained using AutoML. You see a trophy here. And when the model finishes training, you see the status change from queued to ready. And let's click into the model version. You will see the learning curve. You see the decay and some other metrics along with hyperparameters. This is a classification problem. Let's look at a confusion matrix. It looks like the diagonal elements are close to 1. The rest are close to 0. It means our model is able to categorize those different type of news topics pretty well. And sometimes you don't want to just look at the metrics. You want to look at how the model performs on specific data set. And you can play with our PQL query editor. So PQL stands for predictive query language. You can write regular SQL to take a look at the data. So for example, this is one article in our data set. You can also write a predictive query language. You can say predict is target variable. And another cool thing with PQL is you can add a clause with explanation. So it gives you additional information. It helps you with model interpretability. So for example, let's look at this data point, and you can see this column called category explanation. And when we click into it, you have a summary. And I think it's really cool. You can, the green words are the tokens that helps the model makes the decision, and the red are the ones that are not very helpful in this prediction. So it gives you intuition to understand when the model pick up words like accounting, maybe words, or some numbers, is likely to predict this data point into the business news. So yeah, that's a quick demo. And if you are interested in learn more, you can go to predibase.com to request a demo or read some blog posts there. So now I'm going to stop sharing, and I will ask Anne a few questions I had, and then we're gonna go to the questions in the chat. So how do you compare Ludwig AutoML to some other AutoML solutions out there?
Yeah, it's a good question. Yeah, I think there's a fair number of AutoML solutions that will give you a good model. There's, AutoGluon, there's, GCP Auto Tables, there's even AutoSKLearn, but they're targeted at a different design point. So they may be targeted at, giving you a model, but also hosting that model. So you don't have the ability to, be able to manage that model yourself and serve it the way you want and analyze it in detail. They may not give you a standard model. They may give you a model where it's an ensemble. It's hard to, reason about the model. You may not be comfortable with that model because you may want to be able to use a model that other people are using, that there's a lot of experience with. They're not always as efficient in terms of finding the model. So I think, there's different design points, and I think, you can't go wrong with AutoML, but I think there's things that Ludwig AutoML does well that people care about. So same thing with text classification. There's, Google has a text classification system, so does Azure. But again, you may be looking for something where you have more control over the model.
Mm-hmm. Yeah. Thanks for sharing that, Anne. And I think one thing you mentioned during our presentation, which I think is very important when it comes to deep learning, is resource management. And you gave a few very practical suggestions. For example, try reducing the length of the token, and then reducing the batch size. I think you tried a few things there. And I remember when I was training deep learning models, I always get different type of errors, or sometimes have issues with the GPU images, or when I want to do multi-thread training. So do you have a framework you use when you try to debug when there's some memory issue? Like, what are the steps you usually go through?
Right. Yeah. I mean, we feel like we suffered, so you don't have to. So we did try to encode all of these various challenges that we had in keeping the model within the GPU memory, at least for text classification. You may have another problem, and so you'll have to do that debugging. But yeah, it is a good question. So basically, yeah, I guess a lot of how big the memory is. A lot of staring at what's going on in the logs, basically. There's some good tools out there. I haven't done this recently, but there's some good tools to characterize, where memory is going in Python. So we used those. You can find those on the internet. But yeah, it's not an easy job. That's why once you have, let's say you have those insights for image classification, please put them into AutoML and Ludwig so that other people won't have to suffer. Because yes, it is, all these best practices you find through painful debugging of, tedious monitoring of what's going on the GPU memory with tools there. Yeah, it's just a difficult problem.
Mm-hmm. Yeah. And I think a lot of times it takes just some experimentation, like you mentioned, reading to the logs and try some small steps. And I really like what you mentioned is you try one thing at a time, because sometimes if you try two things, you don't know which one actually made the difference.
Yeah, it's always, because these things take a long time, you're always in a slightly greedy mode of like, let me try two things. But
right.
Then even if it works, you're a little bit bummed because you're not sure which of the whether you needed both or what voodoo, you're not sure. So yes, it's difficult.
Yeah, and also keeping, if you're using Ludwig or other platform, you can keep your own log. But if you don't have a way to track the model lineage, so I think the documentation is also very, very important. So the last question that I have for you is, you presented a few data sets. Can you summarize, or maybe beyond those data set, what are some other industry use cases that you think would be a good fit to use Ludwig AutoML or Ludwig in general?
Right. Yeah. I think, any application where you want to use deep learning and there's a large amount of tribal knowledge about how to use it, but it's not encoded in a way that's usable, I think that's a good opportunity for AutoML to step in. But yeah, if you look at the list of models that Ludwig supports, it's vast. So I mean, maybe there's things that are just not very practical to run for at least an individual, but I do think, anything that you can name off the shelf that you would be interested in training for your own use or for your use at work, that when you're not in the business of AI, I think would be a good use case for Ludwig.
Mm-hmm. Yeah, awesome. So now let's look at the chats to see if there's any questions. I think Anarv from our team has answered a lot of questions. And do you have anything that you would like to add?
No, I really appreciate this opportunity, and I'm glad that folks are interested. And please reach out on the Slack channel of Ludwig if you have further things, because we're all out there. And come try it and join us. And that's good.
Yeah, and we are going to release Ludwig 0.7, so there's a lot of updates. Oh, we already released, sorry, and we have a blog post. You can go to the our Ludwig blog on Medium, and we also have blogs on Predibase website. We have a YouTube channel. You can watch this again, and in the future, I will also share more Ludwig related contents on my LinkedIn platform and also future events. Thanks everyone for joining, and thanks again. And this is a great presentation.
Thank you. Thank you very much.